If you've studied any math beyond pre-calculus or so, you've doubtlessly come across this equation called the law of sines. It's an equation that looks like this, and what it gives is a relationship between the angles of a triangle and the lengths of the sides opposing those angles. More specifically, it says that the ratio of the sine of any angle in the triangle and the length of the side opposing that angle is the same for any pair of angle and opposing side on the triangle. And if you're anything like me, then when you encountered this equation in school, you probably just took it as a given and didn't think anything of it beyond that. But it'd be nice if we had a strong intuition for why this fact was true that would apply not only to simple triangles like this one, but also for more extreme ones like this, and ideally even exotic ones like this one. And to illustrate what I mean by a strong intuition, I'll show this image. And if you're looking at the screen right now, then not only do you already know the area of this shape, but you can't help but know the area of this shape. It's impossible not to know its area. And it'd be nice if we could have that sort of strong intuition by which we can see that a fact is true at a glance for a more complicated fact like the law of sines. And if we're trying to do that, then the most difficult part to sort of get an intuitive handle on is going to be the sine, since that's probably the most complicated operation that's occurring in this equation. And to do that, we'll take a look at this image. Now this image gives a visual representation of the sine of a given angle and shows how the sine changes as the angle changes. And here we can see that the sine of an angle, theta, is the vertical offset between the x-axis and the point of intersection between the unit circle and a line passing through the origin and elevated at an angle theta. We also get these helpful visualizations of the tangent and the cosine of an angle, but we won't need those. It's nice that this matches up with the fact that the sine of 0 is 0, and that the sine of 90 degrees is 1. And it even extends to, of course, angles greater than 90 degrees and negative angles, although we won't need that for where we're going to bring this intuition for the law of sines. So I'm going to show a triangle with the angles and the sides labeled. And now, given the intuition we have of where the sine is, we can see where the sine of a given angle, say A, appears on this triangle. The sine of A is here, or at least some scale factor of it. And since the length of this side isn't 1, this isn't the unit circle we're dealing with, that sine will be scaled by a factor of c. And so we see that the length of this altitude can be written as c times the sine of A. But of course, there's nothing special about the angle A. We can also measure this from the perspective of the angle C. And from there we see that this altitude also has length of A times the sine of C. And conveniently, that gives us this equation, C sine A equals A sine C. And through a little bit of rearrangement, just dividing, that gives us one part of the law of sines. To get the other side, the other parts of the equation, no prizes for how you get those, you need only look at the other altitudes of the triangle, perform the same reasoning by measuring it from the perspective of both angles, subtending that altitude, and then equating the two expressions that we get from that intuition. So this altitude is equal to A times the sine of B, as well as B times the sine of A. And this altitude, even though it's not inside the triangle, is equal to B times the sine of C and C times the sine of B. Now, it's not as intuitive that this would be equal to C times, or rather B times the sine of C, because, well, it looks more appropriate to say that this is b times the sine of 180 minus c. That would be more in line with our intuition. But if you think back to how the sine is represented on the unit circle, the vertical displacement that we get from a given angle, say 30 degrees, will be the same if we were to bring the angle over here and look at it for 180 minus 30 degrees. Now it's off the screen because I just coded it that way. But intuitively, or if you look at this on a picture, you can see that the vertical displacement over here will be matched by the equivalent angle flipped across the y-axis. And given that, we now have this very strong intuition by which we can see any triangle here. And by visualizing the altitudes of that triangle, we can almost read off the law of sines directly off the triangle. And that does, in fact, apply to exotic triangles like this one. It applies to extreme triangles like this one, and to obtuse triangles like the one we talked about before. Okay, so that should give you some very strong intuition for why this fact would be true. All the visualizations that I used in this video are interactive. They're hosted on the web. And you can mess with them yourself by going to eulertor.com. You have to be sure to spell it right. And if you do, you'll be able to not only do exactly what I did. So for this video, all I did was click this, and I started going through the visualizations here. But you can also look at the code yourself and edit that code and run it, and see how your code is reflected visually in real time. Okay, so thanks so much for watching, and I hope you enjoy the site.